So today we start, I guess, a new unit of the course, or we start talking about probabilistically checkable proofs. So just as a summary, so we started out this course recalling that so the formalization of a classical mathematical proof is NP, right? So these are proofs with a deterministic polynomial time verifier. Right, and kind of the way you think about it, no, back then we didn't really talk about the prover, but you can imagine that the prover is kind of the source of sort of this witness, which is supplied to the deterministic polynomial time verifier that has the statement that it's checking, right? The verifier is wondering whether x is in L, right? And it does it by just basically reading this witness, which is, again, typically when you talk about NP, you don't really talk about the prover, or you just talk about the witness, but you can think about the prover as the thing that produces it, right? Now, we spent quite a bit of time talking about interactive proofs, where now the polytime verifier has two new resources. So what are the two new resources? Randomness, right? And the other one? Interaction, right? So, by the way, why are we calling these as resources? Because that's what they are, right? So resources are things when you have more of, you can do more, right? So we've seen for both of these that the more you have it, the more you can do, right? And NP really is an extremal example where you sort of have no randomness and no interaction whatsoever, okay? And so, here maybe to put down the picture. Now, because there was interaction, then suddenly discussing the prover was a much more so discussing the prover explicitly is a much more a natural thing to do. Now, so the moment you realize this, it is natural to consider, what other types of resources can be conducive to checking potentially more languages or more efficiently, right? So here we discussed for interactive proofs which languages you can check, up to p-space, can you do delegation or computation, and so on and so forth, right? So you can also discuss, what are types of reasonable resources, right? You don't want to talk about unreasonable resources, but reasonable resources can be helpful to deciding membership in languages. And PCPs, are basically like an orthogonal variation to NP, where now the polytime verifier again has two new resources. One of them again is randomness. Somehow it's really hard to do anything interesting without randomness. And the other one, so it's oracle access to the proof. What is this sound? You hear a sound behind the wall?
It's been there for a long time.
Really? Maybe it's like pipes or like...
I think there's like an electric room or something right behind that wall. There's something there. The prover is trying to talk to you.
The prover is trying to talk to me. So it's using unreasonable resources to do that. I don't know, it's the first time I hear it, or maybe today is the first time my ears work, I don't know. All right, so pictorially, the way it looks like is that it's kind of like NP, where the prover spits out a string. Now we're going to call it pi because it need not be like a plain NP witness. It's really like a string of bits. And now the verifier, rather than receiving it and reading it front to back, is allowed to kind of make this random access queries. Okay, it says, here's a position I, And please give me back the ith symbol. If we're over bits, then this would be the ith bit. It says here's another position j, please give me back pi j, right? And that's maybe a reasonable model. Now, intuitively, what you're trying to capture here are written down proofs, kind of like the classical ones, except that we're going to be interested in a different type of verification that is not just reading every symbol, but we're going to want to sort of previously check the proof. That's why these things are called previously checkable proofs. Okay, so let's try to put down a definition for what this picture means. Okay, at this point, by the time you kind of seen one proof system, all the others are sort of definitional variations. Okay, so it's actually not that hard to formally capture what's going on here. So let's say that. Let's try to define it. But today it's going to be like not a very heavy class. Just for a change. So a Pcp verifier for L is, okay, let's first try to understand syntactically what is it. So before, for an interactive proof, the verifier was what? Yeah, sure, it was an algorithm, but here in this particular case, it was one that can talk back and forth, right? So you can think about it as an interactive Turing machine, a protocol, an interactive algorithm, okay? But syntactically, that's what it was, right? Now, in this case, syntactically, what is this Pcp verifier? Not quite a protocol anymore, right? What's one way to think about it? It has random access to things, sure. Another elegant formal way to think about it is what's called an oracle machine. Okay, so this you can think about it as a Turing machine, right? That is computing. It has a special tape. You can call it the oracle tape, right? And it puts in the oracle tape a request in one step. The request is an index, right? In the next step, out of the blue appears the answer to that request in that that or a different tape or whatever, right? So again, this can be formally defined. It's an oracle into Turing machine. We're going to call it maybe more like an oracle algorithm, okay, doesn't really matter the fact that it's a Turing machine. It could be an oracle random access machine, among other things, right? But the point being is that it's like a special way to access this object, okay, that we sort of denote as an oracle. So, is an
yeah. What's the difference between this paradigm and let the verifier ask the prover I and the prover return I and
Good, we'll come back to that later. Okay. There's a big difference. Okay, so a Pcp verifier for L, maybe let's just say, with completeness C and soundness S is an oracle algorithm or oracle polytime algorithm. In fact, oracle probabilistic polytime algorithm, right? Yeah. Such that, how many properties do I want to write down here?
We don't know. We don't know what you wrote there. How would we know?
For what?
So, two properties.
Yeah, completeness and soundness, right? Which other ones, right? So, completeness. So, okay, so let's try to write it down. So we want to say that when the theorem is true, everything goes fine, okay? So I'm going to say for every x in L, there exists some sort of proof string pi, okay, such that the probability, now we're going to make the randomness of the verifier explicit. So here it is. Now you have the verifier, okay? Now it receives inputs in different ways, right? So the theorem it checks, it just reads it the normal way. So I'm going to put it there, okay? Now the access kind of to the string is an oracle access, right? So you can sort of ask questions to it. So we're going to put it in the superscript to denote the fact that it's a different type of access, okay? And then it also has its own randomness tape, okay? And we say that the probability that it accepts it is at least C. Now for soundness, for every potentially malicious proof, the probability that the verifier will accept this proof on a false statement is bounded above by S. Okay? So notice that this is precisely the definition of an NP, but for the fact that now you get to flip randomness and query your proof wherever you want. Okay, so it's almost, to some extent, the difference between a Pcp verifier and an NP verifier is much smaller than the difference between an IP verifier and an NP verifier, right? Now, we usually we call pi a Pcp. Okay, so Pcp is kind of like super overloaded. It could mean the verifier, it could mean the proof, right? So you'll be clear from context, okay? And intuitively, you can think about it as some, even though the definition doesn't really say that, you can think about it as some sort of robust encoding of an NP witness that allows you to check things with a small number of queries. Which brings me to the question of, I haven't really said anything about parameters, right? So for interactive proofs, we have studied many efficiency measures. We've discussed round complexity, time complexity of the prover and of the verifier, the randomness complexity, right? The amount of communication, publicly versus private. So here, there are some of these complexity measures still apply, others don't apply anymore. So we can define a complexity class, Pcp sub CS, brackets LRQ, subscript sigma. Okay, so these are kind of all the things we might care about. And so C, is going to be, the completeness of the definition that we have here. S is going to be the soundness. Now, what other things might we care about? Well, certainly, notice that while in the NP case, the size of the proof that I give the verifier cannot be more than the polytime, right? Now, need not be so, right? You can actually write down very large proofs that a polynomial time machine could index into. In fact, how large can these be?
I mean, if the verifier is polynomial, it cannot be more than exponential.
Right, can't be more than exponential, right? But it could be as large as exponential. So it is reasonable to think of exponential size PCPs. Cannot be more than exponential because then you can't even index into it, right? You can't even specify a location. So L is going to be the length of pi. But then we also have an alphabet symbol. We have an alphabet here. So as a string in sigma, okay? So we will discuss not just binary alphabets, but larger alphabets as well. So typically, if you don't see this one here, then you should assume that it's over bits. But if you see both of them, then typically this one means like the number of symbols from there, okay? R is going to be the number of random bits of the verifier, okay? And Q is going to be the number of queries. Notice that these parameters make an emphasis of information theoretic quantities. Does it mean that we don't care about the cost to produce the proof or to check things? Check the proof? Of course not. We might at some point talk about those things as well. These are somehow the basic information theoretic quantities that parameterize this class, right? Yeah.
Is R number bits or symbols?
There is no point to discuss the number of symbols for R because this is just in the verifier's mind. So sometimes it is more natural to think of R as being sampled from some specific domain, but really it doesn't affect too much of anything. So R is typically just bits, okay? Whereas what you write down, those are alphabet symbols from some particular alphabet. It's a good question. Okay, so again, we need to make sure that we understand this syntactically well. So notice that in general, an oracle machine might ask queries in very complex ways, right? It might have in mind a decision tree, right? It says, okay, I'm going to query the third location. If the third location is yellow, I'm going to ask, the seventh location. But if the third location is blue, I will ask the 50th location, okay? So such a way of querying the proof is so-called adaptive, right? Some of the locations that you query depend on answers to previous queries. In general, an oracle algorithm could do that, right? Now, we will assume that queries are not adaptive. And the reason is that for many natural constructions, that's basically what comes out. And formally, adaptivity is stronger. Like, just informally, if you try to take an algorithm that makes a certain number of adaptive queries and try to transform it to another algorithm that makes some other number of non-adaptive queries and tries to simulate it. In general, this is not an efficient simulation in terms of number of queries because you have to expand the decision tree, right? But for natural constructions, it doesn't really show up as a thing that is interesting to do. Yeah.
But phi is non-adaptive in the sense that the prover cannot change by the queries of the first.
No, that's not what I mean. That actually has to do with Yunsong's question. What I mean instead is that.
Yeah, I want to make sure that I didn't miss it.
Okay, yeah, no, I'm not discussing that. I'm just saying that the locations, the indexes that you want to ask, only depend on X and rho, but not the answers to any other things. Okay. One other way to think about it is that you can split the verifier into two sub-algorithms. A query algorithm that is only responsible to decide which queries you want to make, and a decision algorithm that collects back the answers to those queries and decides whether to accept or reject. Okay?
So again, just to make sure that so the prover decides on phi, and then we can think about it as the prover goes to sleep.
Yeah. Okay. Exactly. So yeah. So pi is a string, right? It's not a machine, right? It's memoryless. Okay? That's important, and I'll say later. By the way, the reason why today we're going so slowly is that we're going to spend a lot of time with this object, and we'll be doing a lot of. In particular, we'll go up to proving the Pcp theorem, which I'll state later. And so we need to make sure we have a very clear understanding of this class. So now that I've written this one, maybe let's try to play around with some of these parameters to see what do they mean, okay? So let me write down, for example, some, let's say simple class comparisons. So that we get calibrated a bit, okay? So let's suppose that I write down the class Pcp CS 00, okay? So what class do you think this complexity class captures? Okay, I'm saying that some completeness and soundness, but you don't get to flip any coins, and you don't get to ask any queries. Okay, this is P, right? Why not BPP?
Because you cannot flip any.
Because I'm not flipping any coins, right? So this is just P. Okay, that's good. Let's say that I write a Pcp 2/3, 1/3. What comes first? Poly M 0 sigma. So the first one is always the randomness. Okay, but sorry, I forgot to say. Many times, if I don't write if I write 2 arguments, then it's because I'm suppressing L. Okay, when I write 3, okay, it's because I want to emphasize what is L. Okay. So right now I'm saying, suppose I have a polynomial amount of randomness, and I'm making 0 queries. What class is this? BPP, right? Okay, that's good. Okay. Suppose that I write down something like log n randomness. What do I get? P, right? So why? Yeah, like flipping a logarithmic amount of randomness never helps because I can just try it all, right? And whatever I was probabilistically deciding, I can tally up whatever is my gap between the good case and bad case, and I figure it out in polynomial time. Okay, so that's P. Notice that it's remarkable that there is something that I will point out later, that Pcp is about balancing queries and randomness. Notice that keeping queries to 0 and doing a wild change in randomness barely made any difference. Okay, just keep that in mind. Okay, let's maybe throw in some queries. So let's say that I say PCP, and now I sort of come in from the other direction. I put randomness and I put poly in here. What do I get? Right, NP, right? Because I am not, like, whatever queries I'm asking, right? So that kind of defines a proof that I'm reading all, right? So it is an NP witness that I'm reading. And then I get to decide, again, without randomness. So that's NP. Okay. And similarly, like before, if I throw in a logarithmic amount of randomness, then what do I get? Still NP, right? Because it doesn't really matter the fact that I had all this randomness. I could have, whatever witness I had before, now it's just polynomially larger. You can imagine that I had a witness for one random string, another witness for another random string. I can just read them all, right? Okay. Let's try maybe something like this. So we put in log n randomness, one query, okay? And let's say we have bits. What is this? P, okay, yeah, I agree. Can we give an argument of why it's P? Yeah. Yeah, I can try all possible proofs. Why try all possible proofs? Yeah.
The only proofs are like 0 and 1, because you're only reading one bit.
Yeah, but remember that there's some subtlety to this argument that we'll see later. That sort of there's a big difference between one query and two. Okay, when you have just one query, the rest of the proof doesn't matter, right? So you don't really have to think about all proofs. Okay, you just wherever you're querying, that was your only query, right? And the answer to that query is a bit. Okay, notice specifically that I put a 0, 1 here. Okay, this one generalizes to what also? I could put sigma, right? But I need to put some restriction on sigma in order to stay in P. Yeah. Sorry?
Or size sigma is poly n?
Right. The size of sigma should be poly n as an alphabet, right? Okay, because I need to explore all the possibilities that I could have received as an answer, right? I could, like, if I made sigma of exponential size, any particular element inside sigma would have polynomial size to specify. And that could give me an entire NP witness. So I would go from P to NP, right? Make sense? All right, so I have to be careful here, okay? So 0, 1, definitely it's P. And here I can also put or any sigma of poly size. Again, not the element from sigma, the size of sigma. Right? The size of sigma poly size, right?
If it was the size of element, it would be polylog, right?
If it what, sorry?
It was the size.
The size of an element in sigma has size log sigma, which is a logarithmic, right? So in particular, maybe just to highlight it, if I put O log n 1, and then sigma here has maybe exp size, then here is going to be NP, right? Okay, so I'm saying alphabet starts mattering when we start asking queries. Okay, that's not surprising because we're reading into a proof, right? And the answer is an alphabet symbol. Okay, let's try to. So we'll come back to. So by the way, we started at we went from 0 queries to 1. At some point, we'll see that 2 is already quite different. Let's reason about the proof length. By the way, all these inclusions is just so that we can sort of get to reason about sort of what's possible in this model. Otherwise, if we start proving theorems about it, we don't really understand them. So let's say that I have some length. I have RQ sigma, okay? I want to claim that whatever length I have here, there is a certain length that I don't have to go beyond in terms of other parameters, okay? So I want to say that somehow I can just still put RQ here, and there's some number here I can put that I'm saying, look, there's some worst case length that beyond which you shouldn't care. What is that number? To the R, I agree. Why size of sigma?
Because that's how many different variations you play to have. Each one of the bits can be
No, but when I index into a location, the alphabet symbol doesn't matter. The alphabet symbol is just what comes back, right? So this is precisely why we're doing this, just to kind of separate the various things, right? So when I ask a location, that's just a location, right? The alphabet symbol doesn't matter. Okay, so 2 to the R times.
But if they're adaptive, would it matter?
It's adaptive. Okay. No. If they're adaptive, then you have the decision tree to expand, and the decision tree will have a fan out that depends on the size of sigma. But now we're doing non-adaptive things. Okay. So it's 2 to the R times Q, right? Why? Because look, in the worst case scenario, all my query sets are disjoint. How big is my query set? Q, right? Because each time I'm asking Q queries. How many query sets can I have? Well, in the worst case, 2 to the R. So will I ever need a proof that is more than size 2 to the R? No, I will never reach it, okay? So kind of this is sort of the, and it is like a very overcounting, right? Because this is just disjoint sets of answers, right? For each of my queries. We'll see later that sort of when you actually want to construct these things with interesting parameters, it's actually important that the query sets kind of overlap in interesting ways. Okay, but yeah, so maybe we can say, maybe just make it clear. So this is assuming non-adaptive. If adaptive, then the bound is, so I'll write it down here to make sure I don't mess it up, 2 to the R sigma to the Q times Q. Okay, this is the size of like a decision tree when your fan out is, and you can improve slightly here, right? But it does depend on sigma if adaptive. Okay. All right. Let's say in terms of expressivity. Okay, I have say we want to count R. No. Okay. RQ sigma. So could it be that this class, for some settings of R and Q, contains this undecidable languages? I mean, can we put any upper bound on this class? In terms of these parameters? Okay, I give you like a Pcp verifier, right? You have the guarantee that if x is in L, certain things happen. If x is not in L, certain things happen. Now I ask you, take as much time and space as you want. Just decide the damn thing, okay? You need infinite time? Probably not, right? So what kind of machine would you like to use? Like, and how long does it take? Yeah.
Should it be in P-space at least?
P-space, I think that would be too strict of an upper bound. And part of the reason that we don't necessarily know that it's going to be in P-space is that I could have an exponentially large proof, right? And a P-space machine, I can't keep track of it, right? It could be that, so P-space machine, okay, let's just maybe try to address this one. P-space machines, how do they work, right? They have polynomial space, right? And usually they iterate over things, right? But they can't remember very large things, right? So imagine that you had a PCP where you had a polynomial amount of randomness that is indexing into an exponentially large proof, right? In the first iteration, you ask these things, right? In the next iteration, you ask these other things, right? How do you remember consistent answers to the particular proof that you guessed? Right? It's kind of unclear. So another way to put it is that P space equals NP space, right? And NP space, the way you define it is that you have one unidirectional access to an exponential large tape, non-deterministic tape. And since you have unidirectional access, you cannot revisit parts of your non-determinism. And you do need that because the same query might revisit the same location multiple times. So definitely, we cannot put it in P space, but it's we're going up, which is good. So we should go a bit beyond. But yeah.
Is it X?
Sorry?
EXP?
EXP?
Like X?
Well, EXP is at least above, what is believed to be above P space. That is also a little bit too tight, right? Because think about it. Exp, now if you want to deal with non-determinism, you have to loop over it, right? Here we have exponentially sized proofs, and if I want to iterate over exponentially sized proofs, I'm going to need double exponential time, right? So we have to go further up. So what's next? In exp. Okay, so we can probably put this in exp, right? Because in exp, we're going to be able to guess exponentially large non-deterministic thing. What is it going to be? What is going to be the proof, right? And then we're going to use some sort of a machine to go over this proof and quantify whether it's a good proof or not, right? So one way to write it in a parametrized way is to say that this thing is in n time, here I need to make sure I don't mess it up, 2 to the r poly plus q. Okay, let's sort of understand this. Why? I need to guess a proof of size 2 to the r q. Okay? And then I'm going to need this much to evaluate it. Right? Right? Okay. So this is an n time. In particular, once you put it here, you can just put it in double exponential time if you really want. But this is that's a good. Notice that R and Q. So in particular, if R and Q are both polynomial in X, then we get that this is inside NEXP. Okay. Whether it's tight or not, that will be the subject of some other lecture, okay? But we're putting this in NEXP. Spoiler, it actually equals NEXP when R and Q are poly, okay? But it's a highly non-trivial statement. Okay, but we can definitely put this in NEXP, and R and Q are at most poly, so we'll never go beyond NEXP, okay? That's good. See, we're kind of understanding this one a bit better. A couple more inclusions. Let's talk about maybe just the trivial sort of way that soundness behaves. Let's say that I have 1 S L R Q sigma, and I want to improve my soundness error. Okay, I want to make sure this guy goes down. Okay, what's a trivial way to do it?
Double the parameters.
Double the parameters. Yeah, I run it twice. I don't want to just double the parameters. I do something that then influences the parameters. Okay, so I run the verifier twice, or 3 times, or 4 times, some number of times. And I do it with independent randomness, right? So that each of these are IID experiments. Each one, has an independent chance of, catching a problem, right? So this thing will go down as S to the T, where T is the number of repetitions. Okay, so this is inside Pcp 1 to the T. Now, does the proof become bigger? We're using the same proof, right? It's there and just testing it more, right? So it's important, there's just the same, but I am using more randomness and I'm using more queries, okay? And the proof was the same, so I keep the same alphabet. And one can do fancier things using expander graphs. We're not going to talk about it, where you can actually reuse some of the randomness and sort of basically get the same improvement in sound. But the point being is that by straightforward repetition.
Well, we get to reuse L because it has perfect completeness, right? If it had imperfect completeness, then we may need to send a new L or send a new.
Not necessarily, right? Because even with imperfect completeness, here we're making a statement about just randomness over the row. right? So the way you would amplify imperfect completeness is the same way you amplify a BPP machine. You run it more times, you take majority. Okay? But the proof is the same, right? Because see here, this is telling you there's an experiment that only depends on rho and has a certain success probability. As long as these guys are bounded apart by 1/poly, you can sort of amplify it, using sort of BPP style amplification with majority. Okay? Here we're just taking like straight conjunction, right? Good question. Okay, now let's do like a maybe slightly less clear inclusion. Okay, we're going to look at this PCP. So 1s LRQ, and I'm going to say that we can take. So basically, what we're going to explain is we can take a hit in soundness at the in order to get two queries, always. Okay, so we're going to get 1 minus s over q, little bit bigger proof. Okay, R2 and sigma to the q. Okay, we're going to look at this is an important transformation to keep in mind. Okay, in particular, if we do have a constant soundness error, we still have a constant soundness error. Okay, and say that if we are over bits, okay, now basically it's saying that, and we have a constant number of queries, then we're still over a constant size alphabet, and now we're back down to two queries. Okay, there's something special about two queries and larger alphabets. So let's try to prove this one. Actually, maybe I'll make this the first claim of today, since we've been doing a lot of sort of simpler inclusions. Okay. Okay. Any ideas of how we might show this inclusion? I have some number of queries, and now I want to collapse it down to two queries. Okay. Now, the way you do it is, you take some verifier here. We have to build some verifier that reasons like this, right? So how do we construct the new verifier? Let's at least maybe think about the honest proof in the other case. It cannot be literally the same proof, right? Just doesn't parse, right? Look, the alphabet is very suggestive of what might be happening.
Can we consider each alphabet to be q different elements of the previous alphabet?
Sure. Okay. One idea is to just say, look, bundle up your query set into sort of meta query, right? That indexes into k tuples of the previous things, and you get back your answers in one package. A little bit too good to be good enough, right? It's not, right? In particular, the problem is you might query different query sets that are supposed to agree on, on their intersection, right? But in a malicious proof, they may not, right? Because these are physically different portions of the proof, and a prover could have just put different values where they're supposed to be the same. Okay, but we've asked one query. We have another one in our budget. What can I do with my other query?
You can check whether a random query in the original proof matches what it should be.
Yeah, that's a good. I can just do like a consistency check. I can imagine that my proof starts with the previous proof, right? And I'll just pick one of the locations that I collected at random, okay, and ask it in the original proof and see what's there, right? Somehow the proof was already written. It didn't know which query set I'm going to check, right? So to the extent that intuitively, if there are many inconsistencies, then I should be able to catch it with high probability, okay? So now what we want to do is we want to consider proofs, maybe put a capital pi, that look like this. First, it starts with small pi, and then it continues with answers So this is a tuple of things for all my possible random strings. Okay? By the way, here's syntactically a little bit imprecise in the sense that this one is over the previous alphabet sigma, whereas now I have sigma q. Yeah, it's okay. Just put one symbol and then garbage after that. Okay? Or you can pack them more neatly. It doesn't really matter too much. We have this much later. Okay? You could save a factor of q if you want to package them a bit more neatly. Okay? So now we consider proofs that look like this. Okay, and these are the alleged answers, Q-tuple answers to each of my query sets. So maybe just say where pi is in sigma and this thing is in sigma to the q. The verifier, the new verifier, v prime, runs the old verifier, v, to obtain a query set q row, right? Now this is it's a subset of L, right? Of size q. Then what it does, it samples I at random from 1 through q, okay? And checks that two things hold, okay? So one is that V accepts answers a row, okay? And two, that a row is consistent with, I guess we can write it as, pi of q row I, right? So the ith location here will give you an index in the original proof, right? So just you will get it here, and then you need to make sure that sort of whatever symbol inside here is the correct one. Just check it. Okay. That makes sense? All right, so this is the new verifier, okay? Now, completeness, I think we're fine, right? So the honest proof, we'll just write here the previous honest proof, and here it will just provide the correct tuples. Okay. Let's talk about soundness. Soundness is, I think it's a sort of simple but not so simple proof. It's kind of like a rather sort of elementary probabilistic argument, but sort of, again, this is why I want to do these things in one lecture. That so also it's not terribly exciting, but I think it's instructive. So at least when we get to more complicated things, then we're on firm ground. All right, so suppose that we have some malicious proof, capital pi tilde, and of course we can take this malicious proof and parse it as made up of some malicious proof for the first part and malicious proofs for the other ones. Okay? And suppose that this thing convinces v prime to accept with probability, say delta. Okay? What we want to do is we want to construct a proof that will make the original verifier with a certain probability is related to delta to prove this relation, right? That's what we want to do. What do you think is the candidate proof that we might use to show this? Like when I say, suppose there exists some capital pi tilde thing that convinces v prime. Now I have to say, oh, there exists some proof of the old proof system that makes the old verifier accept with high probability, okay? And then, this will give us the relation between these two things, right? What proof should I use? Yeah? Yeah, that's like as good a guess as any, right? Let's just try with this one. If it doesn't work, we'll try something smarter, but this is like a very good one, okay? So we will argue that V accepts little pi tilde with probability at least, with probability S, there's at least a, so it, whatever you invert there, and if I do it here, it should be like y minus q, y minus delta. Okay? This is just like, when you set these two things equal, and you call this delta, and you sort of solve for S. Okay? Okay, so let's just show that. Okay? So S is the probability that V pi tilde x over rho, right, equals 1. Right? This is what that guy is. We need to show that S is at least this much. Right? Now, in order to kind of link this, I need to somehow rewrite this experiment as something about these guys, right? Because all I know is that something about delta, right? I know some event that involves these guys, right? Now I want to learn about this event. So what's a good way to rewrite this event so that it involves everybody? Say that I wanted to put here in the in the subscript, in the superscript, a tilde rho. I can't just put it there, right? Because maybe it's not a good thing. But I can augment the event and make sure it's good, right? Here's maybe. I could write a rho here, tilde, right? But I don't know, maybe that guy is like not a good one, right? Yeah?
Would be given that the old verifier confirms, that this answer is consistent with the old verifier?
Yeah, I can, so also I think I need to put at least here. But I can say, it's okay for me to put something here, by the way, which is what I want to eventually, sort of argue about, provided if everything is consistent, right? So if I have this proof that was making him accept, it's okay for me to put this here as long as I make sure that this value is consistent. I'll just write it as equals a rho tilde of I. Okay? It may not necessarily be I. It depends on the tuple, but I'll just say it's consistent with, right? That's okay, right? I can say that if that guy was accepting, then certainly this thing should be like pretty reasonable, lower bound, right? Maybe there's a few other times where this one accepts, right? Because maybe those are inconsistent places, but at least this should be there, right? Okay.
Do we lose a factor of q since we only check consistency on one random?
Well, I mean, we are losing a factor of q here. Yeah, that's where it comes from, right? But at the same time, if you want to ask more consistency check queries, then you will get more than a 2 here, right? That was the point, right? Obviously, this transformation makes sense only when you're down to a small number of queries. In particular, what does it teach you? That from this perspective, if you really want to go to the smallest number of queries, it suffices kind of to get to a constant, okay? Once you're at a constant number of queries and constant soundness error, then you can always go down to 2 queries, taking a further hit in your constant soundness error, which is going to be worse. And you can enlarge your alphabet a little bit also, right? But the point is like, we don't have to haggle necessarily about the number of queries because then you can sort of jump to 2, right? Now, getting a small number of queries with high soundness, that's the different story altogether, and you won't go through this type of transformations, which are rather silly anyways. Okay, but that's actually, this is not the event that has to do there, right? So there we're checking one guy, right? So it is helpful to flip this over and look at the other side. This is equals to 1 minus the probability that VA tilde x rho equals 0, or that exists some I, okay, in Q, where these guys disagree. Like, I'm just taking the complement event, right? So if here the event that we're looking at, it says accept and everything is fine. The other event says either this guy is not happy or something went wrong. Okay? Okay. Fine, but there's an exists here, right? I can pull it out. Okay, notice this other part of the event has no dependence on I, so it's okay, it just kind of moves through. So 1 minus the sum from I equals 1 to Q, probability rho that VA tilde X rho equals 0, or the specific I is inconsistent. Wait, so far we've only done it's kind of manipulations. Now there is the point. So there we're picking a random I. Okay, how can I relate this thing to the random I?
Q times the probability.
Yeah, it's Q times that, right? Because like 1 over that is like the average, right? So I is random, so with 1 over Q probability, I'll be hitting one of these things, right? So this is literally equal to 1 minus Q times the probability over I and rho that V A tilde X rho equals 0, or pi tilde Q rho I is not equal to this thing. Okay? And this is just 1 minus Q, 1 minus delta, right? Because this is precisely the probability that this guy rejects, right? Okay, yeah, we do this slowly, just so that we understand it. There's nothing much going on. The main point that's happening here is that you're averaging, sort of these events because you're picking I at random, okay? And yeah, you lose a factor of Q because you're doing only one consistency check out of Q things you could have checked, right? Okay, so so that's so I guess trivial, but not so trivial inclusion. Okay. Now let's try to put something in PCP. Okay, let's try to do like a simple inclusion rather than upper bounding PCP. Now we want to say that it's powerful for something beyond P and NP. Let's try to put P space into it. Okay, that's going to be also a rather straightforward thing, but at least this I think will address Yunsong's question of how does it relate to P space. So let's get rid of this part. Okay, simple claim. I'm going to say that P space is contained in PCP poly. I think here I can just put something like 2/3, 1/3. It doesn't matter there. They're not equal. When this actually equals next, we'll prove it at some point. But let's at least show that if you give me a polynomial amount of randomness, polynomial number of queries, then I can put P space into it. Any thoughts of how we can do that? Yeah. Yeah. In fact, any protocol. Okay. Doesn't matter. It's really Shamir's protocol. So that's precisely the idea. So let's try to say it in maybe a couple more lines. First, we're going to use the fact that P space equals IP. Actually, in this case, is a rather useful equality. Okay, and pick a public coin protocol for a P space complete language. Oh, it doesn't matter if it's P space complete, but pick a public coin IP. Okay, here it is, PV. Okay, so I'll explain, we will get to why it's public key in a moment. It's actually not super essential, but it helps to think about it like that. Now I want to write down my pi, right? So what should I put in my pi? The flattened protocol. Now, how do I write a flattened protocol? Yeah, it's like a tree, right? So I put the answer that the prover could have said on my, first message. Okay? So I could have sent him, I'm using R because it's a public key protocol. So I could have said, hey, here's my randomness, my first message in the public key protocol. So, oh, here's my answer. Or I could have said another thing. Okay, put them all down. Okay? Then, the next time around, the prover already knows R1, right? And I'll tell him, well, what if I said R2? What would you say now? Here's his answer, right? And I continue this way. And at some point, I reach the end, right? So, so that's the proof, and the honest one. The malicious one, whatever it is, I parse it this way as a tree, right? And the verifier for the PCP will, how will it work? It will sample R1 through RK, right? It will query, to get AR1, AR1 R2, up to AR1 through RK, right? And then it will run, VIP on X, and all these answers, right? And the same randomness that I used, right? Now, how many queries am I asking? All right, let me ask first, how much randomness am I using? K bits of randomness? How much randomness am I using? Randomness of the verifier. How much the verifier use? How much does the IP verifier use? Yeah, polynomial. That's why there's a polynomial here. Okay, good. All right, how many queries am I asking? Not quite, right? I mean, I'm querying into different parts of the proof, right? Sorry?
Like a polynomial number of polynomial queries. Polynomial.
Yeah, so first I need to sort out, yes, polynomial. I need to sort out my alphabet. It doesn't really matter too much. I could either think at the bit level, so that each of these queries is actually, querying into blocks of bits, and I count them as bit queries, or I could count them that I sort of query a symbol. A symbol is a prover message, right, of polynomial size. Either way, I'm asking across rounds, potentially a polynomial number of queries over an alphabet whose symbols have polynomial size. Okay, it's an exponential size alphabet. Okay, and I could break it down into bits if I really want. So that's where poly comes from. Now, the reason why I was using a public key protocol was that I can ask the questions non-adaptively. Okay, if I don't have a public key protocol, I don't want to directly flatten a private key protocol. That's okay too. I just need to have it adaptive as a PCP, right? Because even as an honest verifier, I don't know what message to ask next unless I hear first back from the prover. Okay? From a complexity perspective, though, it doesn't make a difference because p-space is just as well captured by public key protocols. Okay, so it can really suffice to consider this. Now, and now comes the question of, what's the difference between PCP and IP? Okay, one way you can think about PCP is an interactive proof where the prover is restricted to behave non-adaptively. Somehow, if you're going to ask him, in one round, one query, and the next round, a query for somewhere else, he's not allowed to kind of react his strategy depending on your previous message, right? So it's kind of, he has committed in advance, to answer queries consistently, right? At the same time, this direction tells you that from a completeness perspective, that's not really like, we can capture IP anyways. So we are weakening the prover, and we're leaving the honest prover just as powerful. So this should suggest that the prover has less of an opportunity to cheat the verifier. This is maybe one way you can think about why we might actually go above p-space. Okay? Some of the prover is helpful, but not too strong, such that in IP, the verifier cannot ask queries. There's no such thing as asking queries in IP, right? Because the verifier has no guarantee that the prover might not change its mind depending on the queries. Okay, and so this simulation kind of makes clear kind of what's the relation between them. Hope that makes sense. Okay. Right. Good. Oh, by the way, what's the completeness and soundness? It's whatever you get from the interactive proof, right? You exactly preserve the completeness and soundness from the interactive proof because this is like a perfect simulation. Yep.
So we could in principle change that to like perfect completeness, right? Pcp 2/3 something.
Yeah. So if you want to consider the specific, amplified Shamir protocol, then you would get something like that, right? And here, more generally, what you get is that you get CNS from some certain IP, you preserve that. Yeah.
Where does MA sit here? Because MA is contained in p-space.
Yeah.
And in the beginning, I thought intuitively, apparently I had the wrong intuition that Pcp poly equals MA.
And it's not true because it
Yeah,
equals next.
No.
So MA is like way over here, right? So MA, you can think about it, of course, in Pcp language because MA says the prover moves first, he sends a witness, the verifier reads it in full, right? And flips randomness, right? So what's happening there is that you don't really have a probability of error, right, in MA. So what am I talking about? Yeah, no. That makes no sense. Sorry. Let's write it properly. So MA with say 1 and S, right? It's contained in Pcp. What do we need here? We need poly, right? And poly, right? Okay. This is just a containment, but it's not an equality. That's all that's happening, right? Once I give you these resources, there are just much better ways to put them to use than to read a witness in full. In particular, by the time I give you this much randomness, you can index in exponentially sized proof and sort of do much more.
My question maybe is there something above Pcp log n poly n that is known to be contained in MA? Like other than NP because it's NP, right?
You want to put log n?
Yeah. So my question is whether there is some like Pcp, something higher than log n, poly n that is contained in MA. Like we know that Pcp log n poly n is contained in MA, which is contained in Pcp poly. So I'm asking whether there is a better bound from below.
It's a good question. I believe so. Maybe I'll send you an email later. I just thought of some references of people that have looked at probabilistically checkable characterizations of either AM or MA, one of the two. I think maybe Andy Drucker from University of Chicago, but I can send you like some references. I don't think I don't think characterizing MA as Pcp is a simple equality. So maybe better to try to send an email later. But this one is definitely an inclusion, but not an equality. All right, now let's go back to here. All right, fine. So this was just a simple simulation. Now, what I want to get to is to try to state the Pcp theorem. Okay, so at some point, all of this feels like okay, we're kind of playing around with this complexity class. Oh, yeah, that's cute. So where are we going with this? Okay, so the reason why PCPs are interesting is that when you start balancing properly sort of the randomness and the query complexity, you can actually get very surprising statements. In particular, we'll see sort of various PCP theorems. Now, perhaps the best well-known one says that if you give me a logarithmic amount of randomness and a constant number of queries, in fact, as small as 3 over the alphabet 0, 1, then I can capture all of NP. Okay? And so this is a very strong statement. This basically says that I can write down a poly-size proof for something like 3SAT, okay? That I will inspect at 3 random locations. Random, they're correlated, but they're randomly sampled. I will have an error that is just 50%. And what's really surprising is that this 3 and this half are universal, right? This could be like a 3SAT formula of like 1 million or 1 billion or 1 trillion clauses. It doesn't matter. There's some way to kind of write down a proof for its satisfiability that always, with 3 queries and 50% confidence, you can decide it, okay? And maybe to really let it sink, let's prove kind of the poor man's sort of version of checking satisfiability the trivial way, right? So we can prove that you can get a soundness error of 1 minus 1 over m if you're going to sample log m random bits, query 3, and m is the number of clauses. Or let's just kind of put here 3SAT. Okay, let's just try to prove this is not a PCP theorem. Okay, this is just to calibrate. Okay, so let's just try to prove that if you give me 3SAT, I can definitely put it inside this thing, right? What do? I set pi to be what? Satisfying assignment. I put down A1, A2, blah, 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 up to AN. Okay, this is a candidate satisfying assignment. Okay, the verifier will do what?
Ask for a clause.
Yeah, it will sample a clause, okay? And we'll check that clause J is satisfied. Because it's 3SAT, this requires querying the proof at 3 locations, okay? Now, in the completeness case, it will always be right. When a formula is unsatisfiable, regardless of what proof you put as a candidate satisfying assignment, there will be one clause that is not satisfied. That's what being unsatisfiable means, okay? And with probability 1 over j, I will hit it, okay? But notice, like the parameters are pretty much the same, but for like a tiny detail, which is the soundness that you get, right? So this soundness approaches 1 as 1 over m. It's really crappy, right? So it's not bounded away from 1 either, right? But here it's the soundness is fixed, okay? It's a constant, okay? That yeah.
But this protocol already works if most of the classes are.
Good. So in particular, one way to think about it is to go from here to here. What you want to do is to do something that's known as gap amplification. Okay? You want to widen the soundness gap. It's a way to transform a constraint satisfaction problem, something like 3SAT, such that in the completeness case, you move to some other constraint satisfaction problem that is always satisfied. And in the bad case, somehow this transformation amplifies the error and spreads it everywhere. Okay? It's a way of encoding computation, right? So the analogy here is that with error correcting codes, what you want to do is you map messages that differ in one location to code words that differ in almost all locations, right? Here we are encoding computation, okay? It's a semantic analog where just one violation out of m gets mapped to maybe a tenth of all violations, in this case 50% violations, okay? Regardless, right? So this is a way of encoding computation, a way that is robust, okay? And it's really about like encoding things. Notice here there's no encoding, right? we're just writing down a plain satisfying assignment, and we will see as we start proving non-trivial Pcp theorems that that's actually not what we write. We'll write this and other stuff, okay, that will be sort of extensions of this one. We already discussed things like logic extensions. And then we'll leverage this additional information to kind of create these soundness gaps that sort of are non-trivial, okay? So now, this will actually take several weeks to prove. And so we'll start with something a bit more humble, but still very non-trivial. So we'll prove what's known as the exponential size Pcp theorem. It's the sort of the simplest and sort of pedagogically sort of most interesting Pcp theorem. We'll start with that one. It's pretty much the same statement, but you're allowed to put down an exponential size proof. So I give you a polynomial amount of randomness. I'm going to ask, okay, maybe not one, but like 12 queries or something. So some universal constant, okay? And we'll show that we can handle NP with that, okay? Now, actually, one can capture as much as NEXP with this, but sort of doing it with NP, that's it's a particular construction that is very cute, and it gives you a sense of like what's happening inside these Pcp theorems. Okay. So this will take 2 lectures actually to prove this inclusion. Okay, and yeah, I mean, it's a very, very beautiful thing. We'll reuse many of the things we already talked about, like arithmetization. And then we'll start discussing some things that we haven't discussed at all so far, which is this notion of, you may have heard things like property testing or local to global phenomena. Okay, this is a very sort of deep and beautiful part of sublinear algorithms where you're able to sort of query a very huge object in a small number of locations and infer with high probability global structure about it, okay? So in particular, we'll discuss something called linearity testing, okay? We want to sort of determine whether a function is close to linear or not with a small number of queries, okay? And that's like a new ingredient that, really doesn't quite appear inside interactive proofs. What else do I want to say? I'll post, by the way, I post something I post on the website. Sometimes I put some videos. For example, from last lecture, there's a very nice lecture, I think, by Shafi Goldwasser, okay, on zero knowledge. So I encourage you to look at it. I'll post, for today specifically, a link to a playlist. There was just last December, there was an event in Tel Aviv University called Pcp Fest. So it was a lot of high-level talks and maybe more technical talks about PCPs. And I'll try to point out in the next 2 lectures which ones are kind of more relevant to what, but more generally, it's a good playlist to go through. Some of them are just high-level, some of them are retrospectives. So I think that whole sequence of recorded talks are actually a great sort of complement to what we'll do in the next few weeks. Finally, I did want to say is that because PCPs go to NEXP and they capture all these languages, we will see that are actually a very powerful notion of doubly efficient things, right? Doubly efficient things are ones where the complexity of the prover scales with the complexity of deciding in the language. And that was something that's very hard to do with interactive proofs. In particular, there are still many open questions about doubly efficient interactive proofs. In PCPs, the reason why PCPs are so deeply connected with delegation of computation, which is a cryptographic goal that we don't talk about too much in this course, is because many natural constructions of PCPs are already doubly efficient. Okay, so they are like kind of like a very natural tool to use to delegate computations. Okay, the prover will always kind of very naturally follow the complexity of the language that you're proving. Okay. Anyways, so the plan for next week it will be over 2 lectures to prove this first sort of baby Pcp theorem. Okay. And I think it would be a little bit more interesting than a bunch of inclusions, but we had to go through this first. Okay.